Yeah, so thank you for the introduction. So I'm not going to repeat my name, but yeah, I'm talking about randomized specification testing for heap manipulating programs. This is joint work with Benjamin C. Pierce. So our motivation is that we want to catch bugs in low-level software. So this is like things that are critical, so system software, embedded software. And we want to do this by applying property-based testing, which is that given some property, we want to generate random inputs and see if the property holds. And so when we look at applying PBT for heap manipulating programs, first thing first, like we have this random generator. Writing these generators is tedious, so we don't want to require the user to do this. For functional languages, tools can derive these from the types, but void star, what does that even mean? For theorem provers, they have certain preconditions that they can generate these generators for, such as inductive relations, but they don't target programs in languages like C. And so we want to derive generators for C functions where our property is going to be a precondition postcondition pair. And so a really important question is, what is a good program? What is the specification language that's defining this precondition postcondition pair? And so we want something that captures complex memory ownership patterns. We can check it at runtime so we can test it. And we want to be able to generate inputs that satisfy the precondition fairly quickly. And so we will look at separation logic. In particular, we will look at a fragment used by CN, which is a verification tool for C. And so in their paper, they showed that they can capture quite complex ownership patterns. There's also work Fulminate, which we depend on as like our test oracle, which will take a CN specification and turn it into instrumentation that will check that it holds at runtime. So our contribution is automatically generating inputs that satisfy preconditions. And so in general, summing everything up, like our approach is going to be randomized backtracking search. And so Bennet, our tool, will boil down to these steps. We start off with a CN preconditions and some predicates. We will convert that into a generator DSL. We then apply some not so interesting but necessary optimizations to simplify logical constraints, reorder when variables are generated. We then have a notion of size generation, which I won't be able to cover due to time constraints. And then finally, this goes down into a bunch of generators in C code with like no external dependencies. And so what do CN specifications look like? This might be a little bit of a surprise. I'm going to kind of quickly go through this, but I'm going to look at this from the angle of Fulminate. So this is instrumentation. So we have a concrete heap on the right. We have a predicate on the left. This predicate's saying that we have a list of positive integers. We're going to say we give it a pointer, 1, 2, 3, 4. You check if it's null. Take the else branch. We have this primitive called owned, which states that it's exclusive ownership. And how Fulminate would track this is that it will mark the relevant bytes and say that this has been had ownership claimed of it. And so then if something tries to claim ownership a second time, you know that there's an issue. Assertions, it just checks that they hold. And so you end up with writing predicates in this format where you take in pointers or the arguments to your function and you're producing the mathematical representation. And so then we want to have our generator DSL where we have a clear translation from the CN specification, the precondition. We want to satisfy all the constraints that CN expects. So this is logical constraints like the assertion, as well as resource constraints like the use of owned. And we want to have a relatively clear translation to C, though we can only do so well. And so our DSL largely looks like CN, which makes the translation quite trivial. We're going to track when we generate values and place them in memory, which will correspond to ensuring that we have exclusive ownership. We will be pretty explicit about the points that we can backtrack to, which helps us simplify the C implementation. And there's like a whole monadic semantics. I'm not going to cover it in the talk, but it's all in the paper. And so I'm omitting a bunch of things because they will just map one-to-one. So assertions will map to assertions, if-else to if-else. But considering what the previous predicate we looked at, we have this word take. Take means that on the right-hand side, you could be reasoning about resources. And so we will transform this into a let star, which means that on the right-hand side, we're dealing with a generator. So there's some randomness involved. And then in the case of owned is saying that P, we have ownership of some P, where we have some C-type data there. And the data that's there is X. And so rather than reading from P and setting the value of X, we're instead going to generate some X, which is going to be an arbitrary value of that C-type. And then we're going to assign it to location P. And so one thing is that we are going to check every time we assign anything that it does not overlap with pre-existing assignments. And so since each assignment corresponds to the presence of owned in the original predicate, this is going to preserve exclusive ownership because we're ensuring none of these things overlap. And then let star is going to be the points that we can backtrack to, since that means that there's a generator on the right-hand side. There's a slight caveat there, but I'll show it. And so this is what the generator that corresponds to the predicate we saw would be. And so this is largely the same, but suppose we generate some p, it points to some memory, 8 bytes, let's say. We'll check, is it null? We'll generate some arbitrary struct list node. We'll try to assign it to p. And so suppose, previously we had like 2 blocks. Suppose it only has 8 bytes, but we need 16 to be able to perform this assignment. And so what we do is we will backtrack. In this case, since p is an argument, we will backtrack to the caller. And we will, importantly, carry information with this failure and say that we need at least 16 bytes. And so p will be reallocated with at least 16 bytes. And so then we re-enter this generator. We're going to generate another arbitrary struct list node. Important to note is that it's not a coincidence that the value of head here is -10, and it was -10 before we backtracked. After we backtrack to reallocate specifically, we will always make the same choices. This is because otherwise you would end up skewing the distribution of outputs to be smaller, because the larger an input that you're trying to generate, the more likely you are to backtrack to reallocate, which would regenerate a bunch of values. And so you have to really make sure that you make the same choices. And so we want to guarantee exclusivity, and so we'll do a very similar thing to what Fulminate was doing when it was checking the predicate. We will instead mark when we assign to a location to make sure that we never assign to the same location. And so then we will check an assertion. If an assertion fails, we will once again backtrack. In this case, since we backtracked before an assignment, we're going to unmark the assignment. So we went to the let star n. And we are also going to carry information when a logical assertion fails. In this case, it's going to be the variables we like quote unquote blame. The approximation we do is that we just take all the variables that are mentioned in constraint. So in this case, n.head greater than 0, the only variable mentioned is n. So we're going to try to regenerate n. And so if you keep doing this, eventually you can generate the same list that we saw with the predicate. And so what are the optimizations? So one thing, it's quite naive, but we break apart a bunch of logical assertions. And so in terms of like the and, this is quite simple. We introduce a syntactic form which does not correspond to anything that appears in CN, which is pick, which is just performing a weighted choice. Technically, what it's doing is it's doing a choice without replacement. So if it chooses one of the generators, that generator backtracks all the way to the top. It will then try a different option and keep going until it exhausts all the options. However, one thing that's important is you actually have to be quite careful when you're doing this. If you look on the right-hand side of how we're dealing with the disjunction, we're turning it one generator into 2 generators, which we're choosing between. However, if E1 and E2 are constraining the output of another generator, there's like a really specific case where we provably know that we're going to make our generator worse, and we're going to result in like more backtracking, and we're going to be less likely to generate an input. And so this is detailed in the paper, but you have to make sure that you do not break apart disjunctions like that in that case. And then there's a reordering pass. We're going to, in varying levels of priority, our first priority is if we see any constraint where we have some variable equals f of some other variables, we want to generate the thing that's on this x after the values into the function. The reason why is because then instead of generating an x and checking if it's equal to this expression, you can just set the value of x equal to the expression. And then as a second thing, we also want to bias recursive generators to be called before primitive ones. And so if you imagine generating a binary search tree, you have a node, you want to generate 2 subtrees as well as the value at the current node. It's cheaper to generate the value at the current node, and so you want that to be generated later so that when you backtrack, that gets regenerated first. And then otherwise, we preserve the existing order. We also will check constraints as soon as possible. So we will take, for example, a constraint over A, B, and C, and move it to right after all 3 of them have been defined. And so then we know as soon as possible if we've failed some constraints, so we can start backtracking. And so I will go straight to the evaluation. So does Bennet work with existing CN annotated code? So we took the CN tutorial, including some extensions that were used in the evaluation of the instrumentation Fulminate. For nearly all the non-buggy examples, we're able to generate 100 passing test cases. Discards here mean that it backtracked all the way to the top, or it exceeded a set time limit. There was only one case where we failed to generate an input, and that's because the precondition required specifically the list 1, 2, 3, 4, 5. And so we did not end up doing that. We did, in fact, discover 2 bugs. There was an assumed fact that was used in the proof of the correctness that for pushing to a queue. And so we discovered a bug in that, and then we also discovered an incorrect base case in one of the extensions from Folinate. And then can Bennet find injected bugs? So we compared against handwritten AFL++ harnesses, which are guaranteeing that the memory shape is correct, but the logical constraints AFL++ is in charge of getting past. Here, if you look at the table, tasks are defined as a bug that we injected, the function that's being tested, as well as versions of specification. This is because for our recursive data structures, there's like many ways that you can write the predicates. We didn't even fully exhaust them, but we cover a decent set of them. And so solved here means that for one of these tasks, the bug was found in all 20 trials. And so in the case of Bennet, we were able to, in all these trials, find all the bugs and do them quite quickly. Now, do our optimization passes matter? Because they're not that interesting. And so in this visualization, which is taken from Etna, which is a work on evaluating PBT, the numbers are these tasks that I just talked about, and they're kind of colored based off of how quickly they're found. And so you can see that if we disable the reordering pass, then in the case of the AVL tree, it will keep regenerating the right subtree before it tries regenerating the value at a particular node. And so out of the 26 tasks, 24 of them we do not find the bug consistently. And then if we disable the lifting pass of breaking apart the logical constraints on this runway simulation, which is the most complex logical precondition we had, then out of the 6 tasks we had, 5 of them fail to be solved consistently. And so the end, we synthesize generators from CN specifications. CN syntax makes this transformation relatively intuitive, and we kind of frame the synthesizing of these generators in an optimizing compiler.
Are there any questions?
Is the
Where exactly the separation logic helps you in this process?
So the separation logic aspect here is just that in the CN language, when it's calling owned, that correlates to a points to. And so take x equals points, takes owned p is p points to x. And so as far as we're concerned, we don't really care that much about the fact that it's separation logic. And so if you have a fragment of separation logic which constrains existential quantifiers where, so there's a paper, Brotherston et al. 2016, I want to say, Popple, which is model checking symbolic heap separation logic with inductive predicates. There's a fragment that they define in there, which is polytime to model check. I believe that fragment's very similar to the fragment that CN falls under. And so technically, this doesn't necessarily require CN's syntax. It becomes a lot more intuitive because of it. But in theory, if you're within that fragment, you can still apply the exact same thing. It's just that you don't have this nice, we turn one thing into a thing that looks the same. You'd be going from a logical formula to a program.
Hi, great talk. You mentioned that one of the examples that you couldn't solve was looking for a very specific list. Do you think if you took the optimizing compiler inspiration even further, you could sort of compile all the way to just figuring out that actually to get that exact list, you just generate the heap with exactly that list by construction?
Yeah, so there's actually a couple, okay, so there's a lot of PBT work which is specifically from Haskell, and so they take advantage of laziness a lot. And so to some extent, in this case, what you can do is you have a recursive predicate, you can unfold it once, kind of interpret it lazily where any recursive call is treated as undefined, evaluate constraints and see if one of them is definitively wrong. And so in this case, that actually does solve the input for that. However, we ran into an issue where there used to be a bunch more optimizations. However, improvements to the runtime meant that the time to actually generate a single input, even if you backtrack a lot, became very small. And so we would have to find workloads, we'd have to find bugs which take a lot of time to to discover, because otherwise, even like a relatively fast pass on the front end, potentially you could find by doing something dumber, but you just like send so many inputs so fast.
Got it. Thank you.
The speaker.